All right, guys. So before we get started, all right, guys. So before we get started today, are there any questions over last night's assignment? Yes, sir.
I lost mine and I'm restarting on it. Is that fine?
That's fine. That's fine. If you have it done, you can get it turned in tomorrow. If you don't have it today, so you can turn it in tomorrow. That's fine. Now, what we're doing today is we are covering something called a biconditional statement. A biconditional statement. Now, a biconditional statement is a conditional statement, or sorry, a biconditional statement. We have one whenever the conditional statement and its converse are both true. If the conditional statement and its converse are both true, we can rewrite it as a single biconditional statement. And what we do is we take away the if-then, if the hypothesis, then the conclusion. We don't write it in that form anymore, and we write it as if and only if. Hypothesis, if and only if, conclusion. Or vice versa. Because as long as it works both ways, we can rewrite it as a biconditional statement. And the big thing with this here is the if and only if.
So we won't be writing like
If then no. Because if we have the conditional statement, if A then B is true, and if B then A, if it works both ways. If both of these are true statements and they work every time, then we can write it as a single biconditional statement. That means they imply each other. Now, let's look at the first one. It's going to make more sense when we look at this here. So the first example that we have is this here. If two lines intersect to form a right angle, then they're perpendicular lines. Because two lines that intersect that form a right angle are perpendicular lines, yes? Two lines that intersect at a right angle are perpendicular. If two lines are perpendicular, they do what? They intersect at. So no matter which way we set this up, it is true. It works both ways. And since this does work both ways, we can say two lines intersect to form a right angle if and only if they are perpendicular lines. Because we can write this as a biconditional statement, we take the if and then out and stick if and only if in the middle. And that's it. Questions on this here?
So we literally just like tear it in half and then stick the if and only if in the middle.
Yep. If an angle is a right angle, then its measure is 90 degrees. Well,
Angle is a right angle if and only if its measure is 90 degrees.
yes. Because if an angle's measure is 90 degrees, it means it's a right angle. But we could say it either way, because if an angle's measure is 90 degrees, then it's a right angle. And that's a true statement. And we can also say this one here, if an angle is a right angle, then its measure is 90 degrees. It works both ways. The conditional and converse are both true, so we can write it as a biconditional statement with if and only if. Questions on this here? Are you ready for the next one? two line segments have the same length. So if two line segments have the same length, then they're congruent segments. That's true, yes?
Line segments have the same length if and only if they are.
Because we can say it both ways. Because if we talk about the converse, if two lines are congruent or are congruent segments, then they have the same length, which is true. So two line segments have the same length if and only if they are congruent segments. Questions on this here? You ready for the next one? Rewrite the statement as a single biconditional statement. If you can run for president, then you're at least 35 years old. If you're at least 35 years old, then you can run for president, yes? So what would the single biconditional statement be? Yes. How else could we have written this? It sounds funky going the other way. If and only if you can run for president. I mean, it logically, by the statements that we have, that is true. Grammatically, it sounds funny because we want to say if you're at least 35 years old. Any questions on this here? If Mary is in theater class, then she will be in the fall play. If Mary's in the fall play, then she is in theater class. Yeah. Mary's in theater class if and only if she's in the fall play. So we can do it either way.
Yeah, that's what I'm saying.
If Mary's in theater class, then she will be in the fall play. If Mary's in the fall play, then she must be in theater class.
Yeah, that way.
Could we remove the first if and put Mary is in the theater class only if?
Mary is in the theater class. If and only if she is in the fall play. Yep. But what's interesting with the biconditional is they both imply each other. For it to work, both have to be true. But for this here, they are making it a requirement. You can't take the class without being in the play. Yep. Questions on this here? Okay. Now, with all of these here, and especially once we get into more rigorous kind of mathematics, they do these based off truth tables. With P implies Q and Q implies P, where we're just talking about a set as a whole or different groups. And our normal conditional statement can be one of two things. It can either be true or false. Because our first part, our hypothesis can be true or it can be false. Now the conditional or our conclusion could be true or false. So any combination of true and false that we can have with our hypothesis and conclusion, P and Q, can be given as this here. So we could have true and true, true and false and true, or false and false. Now, if both statements are true, the statement itself is going to be true. Because if the hypothesis is true and the conclusion is false, or sorry, let me back up. If the hypothesis is true and the conclusion is true, the whole statement would be. If the hypothesis is true and the conclusion is false, the whole thing is. If our hypothesis is false and the conclusion is true, the whole thing is. True. If the hypothesis is false and the conclusion is false, the whole thing would be. True. Because if our starting hypothesis, what we're starting with, is false, it doesn't matter. And the conclusion is false. We have nothing to stand on anyways. It's pretty much if this class is currently in Texas, then we have a test tomorrow. Are we in Texas? No. I mean, the whole statement doesn't make any sense to begin with, so the whole thing is true for the overall value. But whenever, guys, up here, whenever we're talking about proving a statement, true or false, we always pick this one here, or the top one, are the main ones we focus on. And when we're trying to make proofs, and mathematicians are proving statements or theories or hypotheses or these theorems, we're focused on these two here. Whenever we go through, or you go through to try to prove a statement, we want the hypothesis to be true. Because if the hypothesis is false, it means nothing. Because if the hypothesis is false, the whole thing is true every single time. But we want the hypothesis to be true and then determine if the conclusion is true or false. Because if the conclusion is false and the hypothesis is true, the whole thing would be false. And this is some of the ways that we would work through trying to determine if something is true or false, if something works, if a number is contained within a set. Now, the one below it, the converse. Converse is what? We just switch the hypothesis and conclusion, yes? Now, so our p-values, if it'll let me erase, and Q are still the same. We still have our true, true, false, false, and true, false, true, false. So true implies true. So we're going this way. True implies true is going to be true. The next one, false implies true. True. Because whenever the hypothesis is false, it's always true. It's always a true statement. As weird as that sounds. The third one, true implies, which is false. And lastly, false implies false is true. Whenever the hypothesis is false, the whole thing is true. So we have this here. We have the conditional and the converse. Questions on this so far? It's a little weird, but now we're going to make the inverse. Well, our starting statements for true and false are going to be the same as they were. Because P is true, true, false, false. Q is going to be true, false, true, false. Because that's what we've just had so far, yes? Now the inverse, we are negating both P and Q. We're doing the opposite. Because we have not P and not Q. So if we do not P, so it's switching it. So instead of the first two would be false, false, and the second two would be. And we would flip Q as well. So the inverse is not P implies not Q. So false implies false is true. Because whenever the conditional statement is, or the hypothesis is false, the whole thing is true. Which means the next one, false implies true, is, because again, whenever the hypothesis is false, the whole thing is true. Yep. So the bottom one would be indeed true, and the one above it is false. Because true implies false is false. True implies true is true. Whenever the hypothesis is false, the whole thing is true. Doesn't matter what it is, because if the hypothesis is false, the whole thing becomes true. This is also why, if y'all remember back to probably 8th grade science where you did the scientific method, testing a hypothesis, where you formed a hypothesis and then tested to see if it's true or false. Yes? It might have been 7th. I mean, we made a prediction, and we tested to see if the prediction is true. That's all this is, because if the prediction is false, it means nothing. It literally means nothing. So it's kind of just saying, okay, the whole thing's true. Now the last one, because we had 4 of them, is the contrapositive. Well, we're negating Q and P. So it's just the opposite. Make sure, because again, I think they flipped Q and P on y'all. To make it work a little better. So the first one, false implies false, is true. Next one, true implies false. False, yes. Next one, false implies true. And the last one, true implies true, is. Now, there's more that we can do, but I want to look at something first. So our conditional statement that we had, the first one that we did, going from the top to the bottom was what? True, false, true, true, yes? What we said yesterday was that the conditional statement in the contrapositive will always have the same truth value. This here is just proving that, because those two will have the same. Now, if we look at the inverse, it was true, true, false, true, yes? What were the values for the converse? True, true, false, true. Because again, we said the inverse and the converse will always have the same truth value. And again, this is kind of showing why. Questions on this here? And we could do more of these, but we're not.